Good morning, everyone. Before talking about RBO and ties, I would like to thank the SIGIR committee for supporting my presence here with the travel grant. But as we all know, in information retrieval, we have rankings almost everywhere. We rank system, documents, topics, or terms. So let's consider a generic pair of rankings, a longer one and a shorter one, where the capital letters are just generic items of these rankings. And we might often want to compare similarity to understand how these ranking criteria are similar. One of the most used similarity measure in this regard is RBO, because it handles non-conjoint ranking, and beyond being also head-weighted, is defined for infinite rankings. Originally, it was defined as a sum of agreement of increasing depth, weighted by a parameter P. And this agreement is expressed as a ratio between an overlap of depth D and the depth. So if we take a pair of ranking and we fix a given depth, we are going to just compute how many items are overlapping and dividing by the depth. But we know that we may also face ties in IR. For example, if two systems are ranked with the same precision at 10, or two or more documents have the same retrieval score. And in this case, we wonder, should we really care about ties? And in our opinion, we do, we have to. This is just some statistic computed over the track web track from 2009 to 2014, where we see that basically on average across the years, 72% of the ranking showed some ties, and in each of these rankings we had 26% of document ties on average, which is a lot. So we need to treat ties. How can we do that? Well, first option would be to break them. Then we can choose if to break them either randomly, for example, but this will introduce random noise, or by doc ID, which is what happens with track eval, for example. But we find out that this practice tends to inflate scores. This happens mainly because the tied items tend to be ranked in the same way, which is in alphabetical order. So it's also not a good option. Another option will be then to handle ties directly on the coefficient. So build some coefficient which can handle ties in their formulation. And in this regard, we need to ask, what does a tie mean? If a tie means equality, so that the items are considered as the same, then we might want to choose the RBO definition that was defined in the original paper that we name here RBOW. In this definition specifically, they regarded tied item as if they were all occurring at the same rank, which is the rank of the first tied item. So the rankings in the end will look something like this, where at a given rank, all the items occur. And this deviates a bit from what's the classical interpretation in statistical literature, where usually a tie is regarded as a source of uncertainty. Uncertainty with respect to a strict order that should exist among items. And regarding this problem, there has been some work in the literature from Kendall, which came up with two variants for his coefficient that was tau in that time. The first is the A variant, which is defined as the expected correlation in his case when ties are broken randomly. And it can also be represented, it's also defined as an average across all the possible permutation of the items with ties. So we take the two items, we permute all the possible ties combination that we can have, and then we compute pair similarity between these rankings, such that at the end, the average of this whole pair similarity is the coefficient itself. This is its own definition. And the B version was defined similarly, but with a correction for the loss of information due to tied items. So in this paper, our contribution is about defining RBO with an A and a B variant according to this view of the ties. And how do we do that? We start with the notion of agreement, which can be seen as a ratio between an actual and a measurable overlap. And the value of these two overlap depends on which version of a tie we are computing. For example, if you are computing the original version as it was defined in the paper from Weber, the overlap is just defined as twice the normal overlap divided by the length of the ranking up to depth D, including also the tied items that might occur. The problem with this formulation in the paper was that it's not clear how to implement this agreement in the formulation that normally are used for RBO. And this formulation are a formulation for the prefix evaluation that we are going to describe in a while. And also we find out that the most popular Python implementation available actually try to fill this gap, but the way in which it's done is wrong. And so it might lead to wrong results. Regarding RBO-A, instead we follow the own definition, so it's basically defined as the average agreement across all possible permutations of each of the ranking. But we can now focus only on the actual overlap, which is again the average overlap across permutation. And here the task we dealt was to basically simplify this formulation, so avoiding going through all the possible permutation. And we did so by considering this idea of contribution of an item. So the contribution of an item is actually given by the product of its single contribution in each of the ranking independently. And how do we compute this contribution? Well, we just look at the practical cases, what happens on average. So if we fix a depth, for example, in here equal to 4, then we see that the items in the red tie will appear 1/2 of the time across all possible permutation of ranking L within the evaluation depth, which is equal to 4. And similarly, for the blue tie, those items will appear only 1/3 of the time across all the possible permutations. If we slightly move the depth, then we will see that both M and C will always be included within the depth of the evaluation, so their contribution will be unitary, while for the blue tie, the contribution of those items will be equal to 2/3. The B variant was defined in a similar way, so with the exact same concept of overlap, but there is a very clear distinction in how the measurable overlap is computed. Specifically here, since we are correcting for the loss of information given the ties, we will end up having a measurable overlap which is smaller than D, which means that in general, RBO-B is always greater or equal than RBO-A. But now let's come to how we actually implement these agreements in the coefficient we normally computed. And to do so, we need to introduce the notion of a full ranking. So RBO is defined for possibly infinite ranking, but for practical purposes, usually in IR we truncate them. And the truncation can also lead to different lengths between the rankings. And we will have a seen and an unseen part. The assumption we make on the unseen part will determine also the possible bounds on the values of RBO. Specifically, in the best possible case, we will have RBO max, in the worst RBO mean, and if we somehow assume want to compute a point estimate given whatever has been observed in the seen part, then that's going to be RBO extrapolated. But before going deep into this prefix evaluation, we just define a general RBO which divides the summation across the ranking in 3 parts. The first part only look at the items that are seen in both rankings. The second part at those that are seen only in one ranking, and the third part where they are all unseen. And then we will focus in this presentation specifically on the summation happening at the second summation, because here we can split the seen and the unseen contribution, and it's important because in the unseen part is where we are going to make some assumption. When it's about the minimum, for example, the assumption as it was originally defined in the RBO paper is that all the items are disjoint. So all these items are not matching and the contribution in the unseen part is 0. For the max, on the other hand, we are assuming that all the items actually do contribute, and here is where we diverge from the original formulation of RBO, because we know that if an item contributes in the unseen part, it will have to match another item in the longer ranking L. But that item can be tied. So we need to consider its fractional contribution as we defined the contribution before. For the extrapolated RBO, instead, we are not assuming any specific item to overlap, but we rather have a probabilistic interpretation, assuming that AS, so the agreement measure only in the same part, will be the probability of matching an item in L. But then we wonder which item are we actually matching. And here we introduce a stochastic interpretation, which consider basically the expected contribution of all the items in L that are still unmatched. We tested also this formulation through some experimental demonstration. We took the same track data that I previously mentioned, and here we only consider those 72% of pairs that contain at least one tie. Our scope here was to understand how big is the difference in absolute terms that we might have with RBO when it's just randomly break, when the ties are just broken randomly. And as we can see, there are some edge cases where the maximum difference is 1, but that's given the special structure of track data. Sometimes they are really long data with huge ties. And even though the average is quite small, we can clearly observe that the medium and large differences are quite big, are quite significant. And as a medium differences, we mean differences of 0.01 or 0.1, which somehow, to some extent, means that there exist cases which are not that extreme, where actually the differences matters a lot. And if we put those two medium and large cases together, we have that around 12% of the cases, there is a very significant difference in just breaking ties randomly. But given the limitation of this IR data, we also wanted to compute some synthetic data, where we basically generated smaller rankings between 10 and 100 items, where the average tied items were 54%. And here we can observe even a stronger effect on the magnitude of difference with respect to RBO computed just by breaking ties. It's important, though, to understand that all these values that we are reporting are subject to many different factors of variability. So depending on the size of the ranking, the amount of ties, the location of ties within the ranking, because it's a head-weighted ranking, this difference will be influenced. And especially also if we consider the different kind of coefficient that we compute. So also the version of the coefficient will have an influence on the differences that we observe. So in general, what we want to recommend is to always use a tie-aware version of RBO, and depending on the notion that we have about ties, then we want to take a priori decision on which coefficient to compute. If ties represent equality, then we use RBO as it was defined in Weber. If ties represent uncertainty, instead, we do not want to break them deterministically, because as we show, inflate score. And we also don't want to break them randomly, because it can introduce random noise. And we would rather use RBO-A, because it also has a very nice probabilistic interpretation. And in the end, if we really care about the presence of ties and we want to correct the coefficient by that, then we should use RBO-B. We also provided a Python and R implementation, and they are publicly available online. Thank you.